Greetings. So, we come to another impactful part of Maxwell's theory. Not that there has been any less that we have already discussed so far, but it grows even more. And we will consider Maxwell's equations. We will see how easily the wave equation is developed. So, we pick two of Maxwell's equations, one coming from Faraday lens and the other coming from Ampere, all right. These are the equations for vacuum. So, we will consider electromagnetic fields in vacuum and take the curl of these equations. So, take the curl of E. So, on the right hand side you get the curl of B, okay, and the curl of E is given by these two terms on the left hand side, of which the divergence of E goes to 0 in vacuum, okay. And now the curl of B we know from the other equation from Maxwell, from the Ampere-Maxwell equation, it is given by the time derivative of the electric field. So, put that in and now you have got a relationship between the space derivative of electric field and the time derivative of the electric field. Okay. The second order time derivative and the second order space derivative, these are related by this equation, which you recognize is the wave equation. And you can get an exactly doing the same type of trick on the other equation, on the Ampere-Maxwell equation. You will get an identical equation for the field, for the magnetic field B. So, you have got these two wave equations, and this is really incredible, because whenever you talk about wave, you know that wave carries energy. Okay, wave carries energy. You can have the energy transported from one end to another end, okay, by tapping over here and then set oscillations which will which are like these small tiny simple harmonic oscillators which oscillate about an equilibrium point and they nudge the neighboring point, okay, like you do in a crowd, and you nudge it and then the next point starts oscillating and then it nudges the next point, all right, and then that is how the disturbance propagates. You may have longitudinal waves, you may have transverse waves, right. So, the oscillations are orthogonal to the direction in which the nudge itself propagates, right. But here in vacuum there is nothing to be nudged and nothing that will nudge, but you do have the same phenomenon, which is the propagation of electromagnetic field. So, this is the wave equation, and what has been achieved in this is also the decoupling of E and B, because in the original Maxwell's equations you have got the curl of E given by the time derivative of B. So, those equations are coupled, you have decoupled them, and this is the standard technique in differential equations, that when you have coupled differential equations you often go to higher derivatives. So, from first you go to the second and then you have a chance of decoupling them. If that does not happen, you may have to go to the third derivative and so on, so sometimes to the fourth. So, you may have this is a common technique in differential equations, and this has been used here, and what is achieved is not just the decoupling between E and B, but the discovery of the of the wave phenomenology of the Maxwell fields, of the electromagnetic fields, and both the equations can be written in a common form. They have got exactly the same form. The operator in the box is what is often called as the box operator, or the D'Alembert operator, and it operates on the vector field V, which is a function of space and distance r and t, and this vector field V in the two cases of interest to us are respectively the electric field E and the magnetic induction field B. Okay? So, these are the two fields for which you have these two wave equations, and the solution to the wave equation is very straightforward. It is given you get sinusoidal wave solutions. So, sine or cosine does not matter because they are just phase shifted from each other. All right. How do you know that these are appropriate solutions? What is the big deal? You put them in the original equations, take the first derivative with respect to time, the second derivative with respect to time, do the same with the gradient operator, and check out for yourself if the equations are valid. Okay, it's straightforward to do that. Notice that in the arguments of the sinusoidal functions or the cosine functions, if you like, there is a constant factor delta. And this delta in the solution for E may or may not be the same for the delta in the solution for B. We have no reason to assume that they are the same. So, we take care and write them as separate. If they turn out to be equal for some different reasons, be it so, but at this point we use different symbols for these. So, one we subscript with E and the other with B. So, we can ask, what is the surface of constant phase? So, the phase is given by the argument of the cosine function, which is k dot r minus omega t plus delta, right? And the surface of constant phase is given by k dot r minus omega t plus delta equal to constant, right? K dot r is k r and the angle, cosine of the angle between k and r, right? Because we do not know what is this angle, so we write it as k dot r in general. If you take r to be the direction of k, then it will be like kz or kx or ky or whatever is that variable along that, all right. So, let us just take it to be z, just for the sake of a tentative discussion. So, if you have a term, if the argument is like kz minus omega t, so the argument is kz minus omega t plus delta, and when will this be a constant? When the differential of kz minus omega t goes to 0. So, the differential will be k dz minus omega dt, differential of delta, the phase constant will go to 0, right hand side differential goes to 0. So, k dz will be equal to omega dt, okay, and that tells you what is d omega by dz, or dz by dt, that will tell you what is dz by dt, and that will tell you whether z increases with t or z decreases with t. If it increases with t, then you have got a plane wave which is propagating in the direction of z. If dz by dt is negative, you have got a plane wave which is propagating in the opposite direction, right. So, you can see that you are having a plane wave solution, but you also see that the argument shifts with time. So, it is going to be a plane wave which is a linear function of time, which is why it is a propagating plane wave, it is a travelling plane wave. So, this is a plane wave front, we know that it is a travelling along a particular direction. We still do not know if delta E and delta B are equal, they may or they may not be. So, there are actually I have written only one equation, but there are two of them, one for E and one for B, and you have got this plane wave, so that the wave front on which you have points at the same phase. So, that is what constitutes the surface of constant phase. So, that is the surface of constant phase which is propagating along one direction and as a linearly with time. Okay? So, this is the kind of solution that you get, and you have delta E and delta B. So, the e to the I delta E I absorb along with E0 and write it as E tilde. So, E tilde contains the delta E. Likewise, the B tilde contains the delta B. Okay? So, we have rewritten this in terms of complex amplitudes E tilde and B tilde. Okay? And we are now asking if delta E and delta B are equal. We have still not answered that. So, now you will operate by the gradient operator, and the result of the operation by gradient operator will be like multiplying the operand by Ik. Okay? And it could be the divergence or the curl, or in some cases it may be the gradient of the operand is a scalar function. And the result of the operation by del t is going to be completely equivalent. So, I do not write this as equal to, but as equivalent to, because the effect is the same, not that the two sides of this equation are the same, they are not. One is a differential operator, the other is a vector. Okay? So, the three lines representing the equivalence is to emphasize that these are not equal. Okay? And using this, if you now take the divergence of E and the divergence of B, you get these relations quite easily. What do you find? That K dot, the direction of the electric intensity, is always 0, which means that the two vectors are orthogonal. Likewise, K is also orthogonal to the direction of the magnetic field. So, the electric field and the magnetic fields are both orthogonal to the direction in which the wave is propagating. Okay? So, the orthogonality is now popping out of this relation. So, you take this equivalence between the operator del and Ik and use it for the two curl expressions, and then use the equivalence between del and del t and minus I omega, and what do you find? That the magnetic field is orthogonal to the plane of K and E, because the cross product of K and E is in the direction of the magnetic field, and the cross product of K and B is in the direction of the electric field. So, E is orthogonal to the plane containing K and B is perpendicular to the plane containing K and E, and now you have already discovered in the previous slide that K itself was orthogonal to the two directions of the electric and the magnetic fields. So, now you know that the electromagnetic wave is a transverse wave with E, B and K all orthogonal to each other, and the electric intensity direction, the magnetic field direction and the direction of propagation all being orthogonal to each other, and they form a right hand system. Okay? The directions, when you turn a right hand screw from E to B, it will move forward in the direction in which the wave propagates. So, let us get some more physics out of this. This time we will use the equivalence of del by del t operator with minus I omega, and we use it from on these two equations, K cross E and K cross B. And what you get from these two symmetric relations, from the left you get the ratio E tilde by B tilde, and from the right you get the same ratio E tilde by B tilde, but the other side of the equation are different. You have omega over K on the left and K over mu 0 epsilon 0 omega on the right. So, these two must be equal. Now, that is amazing. K over mu 0 epsilon 0 omega must be equal to omega over K, all right. which means that c square is equal to 1 over mu 0 epsilon 0. Now this is shocking. You got the speed, and we discussed this point when we discussed relativity, that speed is always something that we measure with respect to an observer, okay? And with respect to the speed of an object with respect to one observer is not equal to the speed with respect to another observer if the second observer is moving with respect to the first observer. The difference in velocities have to be adjusted when you do Galilean transformations. But now we find that 1 over mu 0 epsilon 0 is equal to c square. Now this is an incredible result which needed the brilliance of Einstein to come up with the special theory of relativity. It is sitting right here. That if the speed of light is the same, speed being distance over time, distance must change and time must change. So that is what led Einstein to time dilation and length contraction. Okay, the special theory of relativity has its roots right on this screen here. Okay, that the speed of the wave motion is given by properties of vacuum, just 1 over epsilon 0, right? That is what determines the speed of light. So 1 over square root of mu 0 epsilon 0 is c, and c is a real number. So E tilde over B tilde, which included the phase factors delta E and delta B, that has to be a real number. So delta E must be equal to delta B. So they are in phase. Okay, so until now, for the sake of generality, we considered them to be in different phases, but now we see that they are actually in phase, and our conclusion is that the E electric field, the magnetic field, and the direction of propagation are all orthogonal to each other, and they are E and B are in phase. So you see that the nodes of E and B are at the same point. They rise together, they fall together. Okay. And this speed Maxwell calculated from the properties of vacuum as were known, and the speed of light is estimated, it is revised periodically depending on how accurate measurements are carried out. But comparing it with the velocity of light as was known at the time, Maxwell said that this velocity is so nearly that of light that it seems we have a strong reason to conclude that light itself is an electromagnetic disturbance. So not only is the subject of electricity unified with the subject of magnetism, but it is also unified with the subject of optics and light. It's all the same, whether it is optics, light, electricity, magnetism, you're talking about the same phenomenology. And then the frequency doesn't matter, so whether you're talking about ultraviolet radiation or X-rays or gamma rays or infrareds on the other side, it's all the same physics, the same Maxwell's equations, all right? And this is an electromagnetic disturbance in the form of waves propagated through the electromagnetic field according to laws of electromagnetic theory. So this was Maxwell's conclusion. So this is the electromagnetic spectrum, as you know, and it's good to very quickly recognize the order of magnitude of the frequencies and wavelengths, because the speed of light is constant. What we call as optics is is the light that we see, all right, and that is a small part of this whole electromagnetic spectrum, the visible part of the electromagnetic spectrum. And any wave phenomenology was understood to be associated with a medium. Like I said that, okay, you can transmit energy from one point to the other point by tapping it here, and then it is this nudge which propagates. Okay? But then there were these experiments carried out by Michelson and Morley in 1887 in which they expected to measure the speed of light to be going in the direction of the medium and orthogonal to it, and expected that the speed of light will turn out to be different, and it didn't happen. So the conclusion was that okay, you really don't need any medium, and the electromagnetic waves would in fact propagate in vacuum. But then vacuum is something that we really have to worry about. Means physicists have to understand exactly what is meant by vacuum. Is it really nothing, or is something happening over there? And these are important questions. I'll get to that. And we have seen that the field propagates through a medium, right? And the medium responds to the field. And the response of the medium to the field is contained in the constitutive relations, right? Which is D equal to epsilon E and B equal to mu H, which is what we just discussed in the previous class, right? So vacuum cannot be polarized, nor can it be magnetized, and therefore D will be equal to epsilon 0 E and B will be equal to mu 0 H. Okay? So now the question is, how does energy propagate? What is the mechanism? Okay? Now you have to remember that C is a fundamental constant. So between mu 0 and epsilon 0 there is only one which is independent, because the other is automatically determined by the fundamental constant, which is fundamental constant of nature, which is the speed of light. So here it is immature perhaps to get into more advanced theories, but it is at the same time good to alert you all to those theories, because one has to wonder about what is the mechanism of electromagnetic energy propagation. And when you get into relativistic quantum mechanics, which was formulated by Dirac, Dirac talks about the possibility, the relativistic quantum mechanics accommodates the possibility of the creation and destruction of particles and antiparticles, and this can take place in vacuum. So out of vacuum, particle and antiparticle pair can be generated and can also be destroyed, and you can have this happening in vacuum. And you don't have to worry too much about the energy over which, where is the energy coming from, because quantum mechanics doesn't require you to talk about exact energies, because these processes take place over some time intervals and there is an energy time uncertainty. So you really don't have to worry about it. That is how nature needs to be described. But good that nature needs to be described in terms of the uncertainty principle, which is what accommodates the possibility of the creation and destruction of particles and antiparticles, which can take place in very short times. These particles and antiparticles, they may provide some vehicle for the propagation of the electromagnetic energy. They may also explain how vacuum can provide an impedance for the propagation of electromagnetic energy, because these things are measurable, and I will not be able to go into the details of this work, because this is obviously an advanced topic. It needs quantum mechanics, it needs relativistic quantum mechanics. But if some of you are interested, you may want to see this paper by these authors. The reference is at the bottom. And they talk about the permittivity and permeability of vacuum, the polarization and magnetization of particle-antiparticle pairs that are created in and out of vacuum. Okay, so you may want to read this up, but I will not get into this. So now you do have energy in the electromagnetic fields, and let us ask what is this energy. So, we have discussed this in an earlier class. This was in the unit 1 on electrodynamics. So, the slide that I am showing you is a copy of the slide number 63 of our first unit on electrodynamics, in which we constructed the energy of a volume charge distribution, and we found that this is given by the half volume integral of the charge density times the potential at a particular field point. Okay? And when you integrate this over the whole volume, and then we rearrange these terms, we use Gauss's divergence theorem and so on, so did some manipulation of the terms, and we found that it is given by the energy density is half E square multiplied by epsilon 0, of course. So, it is epsilon 0 by 2 multiplied by E square. So, that is the density. When you integrate it over the whole volume, you get the total energy in the electric field. Okay? So, there is a similar expression for energy in the magnetic field that you can get using the same kind of analysis, and you can then determine the work done per unit time. In a magnetic field, the magnetic field will have to do work to set up a current, because it has to be done against the back EMF, because as you start building a current, okay, the current element will resist this process and a back EMF will be generated, and as a result of this, the rate of doing work will be this back EMF multiplied by the current, okay, and the back EMF is proportional to the rate at which the current is changing. So, that being a back EMF, this rate of doing work will be plus I times di by dt. The proportionality is the inductance of the material. Okay? So, if you integrate this, you get the work done to be half Li square, and notice that this work done depends only on the values of L and I. It does not depend on how long it took to set up that current. Okay? It is independent of that. So, now you have got the flux to be proportional to the conductor, to the current in the conductor. The proportionality is the inductance. The flux is the surface integral of the magnetic field B. So, you can equate the two and you see that the work done, which we knew was half Li square, is given by half phi I times this flux we can write in terms of the integral A dot dl, because the surface integral curl of A is nothing but the line integral of A, where we have used the Kelvin-Stokes theorem. Okay? So, this is the relation that we now have, and I have drawn the current I inside the integral sign. So, I want to remind that I is not to be treated as a vector. It does not add according to the vector law of addition, but it adds according to Kirchhoff's laws and so on. But algebraically over here it works. So, the volume current leads to this work done. If you have a linear current, you have IDL. If you have a volume current, you will have a volume integral, and instead of IDL you will have JdV. So, now let us use Maxwell's equation over here for J, and then rewrite the expression for the work done, okay, and use this vector identity, because curl of B is what you can get from the curl of A cross B. A is the vector potential, B is the magnetic field, and by using this identity you get it in terms of B square minus the divergence of A cross B. Now, you are getting some very interesting result now. So, B dot B is nothing but B square, okay. You write it as two terms. The second term is the volume integral of divergence, which I have now written as the surface integral over a closed surface which encloses that volume. Okay. And if you now integrate over the whole space, since A and B both go to 0 at asymptotic region and at a rate, at a collective rate which is faster than the rate at which the surface element is growing, which also grows as r square, right, but together this overcompensates that. So, the net work done, which is the energy stored, that is the amount of work that you have done, and that where will this work done go? It will go as the energy stored, and that is the magnetic energy stored, which goes as the volume integral of B square dV, and this is therefore the integration of a magnetic energy density, which will be B square over 2 mu 0. So, now you have got the two expressions for the electric energy density, which is epsilon 0 E square by 2, and the magnetic energy density, which is B square over 2 mu 0. So, accordingly you write the overall magnetic energy, which is the volume integral of the corresponding densities, and the total energy is the sum of the two. So, you have to integrate over the whole space of the magnetic energy density and the electric energy density, and the sum of the two is what you can call as the electromagnetic energy density. It has now both the components, the electric part and the magnetic part. And now you can ask, what is the mechanical work done? And this really is an amazing idea, because now we are talking about an electromagnetic energy doing mechanical work. Now, you and I can do mechanical work. I mean, maybe we do not like to do it, maybe we often do not do it, but we can. I can pick up this object and do mechanical work on this, and I can calculate how much work I have done by integrating F dot dl, right. What is the force I applied on it and what is the displacement through which I moved that object, and this is the mechanical work. This is mechanics, and now we are talking about the electromagnetic radiation, light, doing this work. It can pick up an object and move it. Optical tweezers. It can physically do mechanical work on objects, all right. So, what is the mechanical work done by the electromagnetic field on a charge element delta q, in a volume element delta tau, over a time interval delta t, in displacing it through a displacement vector delta L? This is the mechanical work that we will now investigate. So, this will be done by the work done by the electromagnetic field. So, it is force times displacement, the dot product, right. So, it is delta q into E plus V cross B, and then dotted with the displacement, which will give the work done, right. This is the total mechanical work done. Okay. So, we were thinking of mechanics and electromagnetic phenomena as completely different things, but now you are actually determining the mechanical work done by electromagnetic energy. And by rearranging these terms, as you can see on this slide, you the magnetic field does not do any work, because you get a term V cross B dot delta L by delta T, but what is delta L by delta T? It is the same thing as velocity. So, you have got a triple product V cross B dot V, triple product, two of the vectors are the same, so the box product goes to 0. So, the magnetic field does not do any work. And then you have got the E dot V term. So, E dot V delta T, all right. Delta Q is nothing but rho times delta T, the charge density multiplied by the volume element. What is the velocity V? It is the current density vector divided by the charge density. Rho V is equal to J. So, delta Q has got rho in the denominator, V has got rho in the denominator because V is equal to J over rho, right, and the two rho's in the numerator and denominator cancel, and delta W is equal to delta tau E dot J delta T. Don't forget the delta T on the right hand side, because if you divide both sides by delta T and then take the limit delta T going to 0, you get the rate at which work is done, del W by del T. Okay? So, this is delta W, and the rate at which work is done is given by del W by del T volume integral of E dot J. Vector algebra, vector calculus, but very important physics coming out of it. So, never dissociate mathematics and physics. Look into these equations and see what kind of physics is coming out of it. So, you are doing a volume integral of work done over unit time per unit volume, which is actually the power delivered, right. The rate at which work is done is power. So, this is the power delivered per unit volume, right. Why per unit volume? Because J is the current density. So, there is a per unit volume element over there. Okay. So, this is the power delivered per unit volume, and now we can use Maxwell's equations over here to write J as del cross B minus del E by del T term, which is the Faraday's correction term, alright, and the two terms we can write these as separate integrals. So, let us do it here. But then you have got the E dot del cross B, and you can get this from the divergence of the cross product of E and B. You have got E dotted with the curl of B. So, get the divergence of E cross B and subtract that contribution. So, now you have got the rate equation, and now you have got three terms in which one is del cross E, which is nothing but del B by del T with a minus sign from the Faraday-Lenz Maxwell relation. And now you see that there is some symmetry which is popping out of these equations. From the first term you are getting a B dot del B by del T, from the last term you have E dot del E by del T. Okay? And both can be written as time derivatives of the corresponding field squares. Okay, because del by del T of B square will be 2B del B by del T. Same thing with E. Okay, and because of that factor 2, you have a half factor which is coming in common from the first and the third term, which I put together in the last equation. All right. So, in the first volume integral you have got a factor of half. You see where it is coming from? It is coming from the time derivative of B dot B. So, you get B dot del B by del T plus del B by del T dot B, which is the same. So, you add the two, you get a factor of 2, and you need only half of it. So, you have got the volume integral of the time derivative of B dot B and E dot E scaled appropriately by 1 over mu 0 and by epsilon 0, and the other term is the volume integral of the divergence of a cross product of E and B, and that we know, we have done it so many times, can be written as the surface integral using the Gauss's divergence theorem. So, having done that, we now recognize that we are getting, we are understanding how energy is propagated, because this is the rate at which work is being done. Okay? So, let us rewrite this expression in terms of the electromagnetic energy density So, I combine the magnetic energy density and the electric energy density together to get what is the electromagnetic energy density, which I write as the lowercase u with subscript EMED, the electromagnetic energy density. All right. The subscript uppercase M on W is the mechanical work done. Okay. And what this equation is telling me is that the rate at which mechanical work is done on the charges by the electromagnetic fields is equal to the rate of decrease in the total energy stored in the field. Why decrease? Because there is a minus sign. Okay. So, here this is the minus sign I am referring to. It is the decrease in the total energy. This is the total energy. This is the energy density integrated over the whole volume. Okay. So, this is the total energy which is depleted because of this. This is the minus sign, but then there is some more which is depleted, which is given by the rate at which the electromagnetic energy, whatever is not depleted, it flows out of the region. Some of it will escape, and that is given by the surface integral, because this is surface integration over the whole surface which encloses this. So, whatever electromagnetic energy propagates and crosses this surface also is a part of that total depletion. Okay? And this is the rate at which mechanical work will be done. So, the signs are very important over here, and this is what is called as the Poynting theorem after John Henry Poynting. This is a very interesting character. Basically, the theorem that we have seen is no more than an energy conservation theorem, also momentum conservation theorem as a matter of fact. So, because it tells us that the electromagnetic energy, when it flows into a region, it does some work on some charges over there. How much is the work that it does, at what rate does it do, and whatever energy is not expended in doing this work escapes that region. Okay, so it is a conservation theorem, and the reason I mentioned that Poynting was a very interesting person, because look at his works. He wrote a textbook on physics. He wrote a textbook on Earth, its shape, size, weight and spin. Okay. And then amazing things. I mean, his contribution is to such diverse subjects. And at the top, in 1884, he wrote a book on comparison of fluctuations in the price of wheat and in the cotton and silk imports into Great Britain. Okay. So, from commerce to astronomy to electromagnetic theory, an amazing contribution. So, this is the Poynting theorem, and the vector E cross B over mu 0 is what is called as the Poynting vector. And in terms of this vector, the expression that we had on the previous slide can be written in a much more compact form, but not just compact, in a much more revealing form, because some nice physics comes out of it. So, it tells us what is this Poynting vector. So, remind yourself that Wm is the mechanical total mechanical energy. So, it is the integral of the mechanical energy density. Okay, when density is integrated, you get the sum total. So, W is the sum total of the integration of the mechanical energy density. The uppercase Um is the sum total of what you get when you integrate the complete electromagnetic energy density, which is the sum of the electric energy density and the magnetic energy density, which we had on the previous slide. All right. So, that is what you have done over here, and essentially what you get is that the time derivative of the mechanical energy density and the electromagnetic energy density plus the divergence of the Poynting vector goes to 0. And this equation would remind you of the equation of continuity in fluid mechanics, right? What is it telling us? That the electromagnetic energy flows much the same way as the equation of continuity describes the flow of charges or the flow of matter. Okay? Flow of charges when electrical charges are flowing in a conductor, for example, all right? And that is what gives you the divergence of J. That is what gives you the Kirchhoff's laws. So they are all connected. And electromagnetic energy flows exactly the same way, that in conformation with the equation of continuity, just the way mass or charge flow is explained. So this is the Poynting vector. The energy density, the electromagnetic energy density is the sum of the electric part and the magnetic part. Now remind yourself that at the beginning of this class we showed that E over B is equal to C, C square is 1 over mu 0 epsilon 0, right, which essentially means that the electromagnetic energy density is given by the square of E times epsilon 0. So between the two there is only one fundamental quantity between epsilon 0 and mu 0, because the other you can get from the speed of light, which is a universal constant. So this is the expression for the electromagnetic energy density, right, and it sums up the contributions from both the magnetic parts and the electrical parts, right. This is the flux density. We have already noted that the phases delta E and delta B are the same, and you can now actually work out this cross product, which will be E cross B. So it will be EB and in the direction of K. So it is in the direction of propagation of the electromagnetic energy. So this is the momentum which is being propagated, not just energy but also momentum, okay. And the energy transported per unit time per unit area is given in this energy density. So this is the Poynting vector, and essentially it represents the power transmitted per unit area, okay, because it is the energy flux density per unit area per unit time. So it is the energy flux density per unit time is power, and per unit area is what it is, all right. So you have got the Poynting vector, and if you look at the dimensions you will see that these are appropriate. You get the power over area to give the correct dimensions of the Poynting vector. So you can get it from doing straightforward dimensional analysis, and the dimensions of S over C square, not S itself but S over C square, or 1 over C square is nothing but epsilon 0 mu 0. So you can get it from the dimensions of epsilon 0 or dimensions of C square, right. Either which way you find that S over C square is essentially momentum density, momentum per unit volume. So that is the momentum which the electromagnetic field propagates, and that is what is represented by the Poynting vector. It gives you the momentum which is carried by the electromagnetic energy. And many authors prefer to write the Poynting vector in terms of E cross H rather than E cross B over mu 0. The two are the same, they are completely equal, but there is some advantage in writing it in terms of E and H rather than E and B. The advantage is that if you have transmission lines in the word characteristic, I do not know why I have two C's. I think my finger when I was typing was too reluctant to come off. So there are two C's, I should get rid of one. Nonetheless, we do not have the time and the opportunity to discuss energy propagation on transmission lines. So you generate power in one town and deliver it to another and send it over these transmission lines. But then there is some power dissipation along the transmission lines, and the transmission lines offer some impedance to the propagation of this. The impedance comes from the self-capacitance and the self-inductance of the transmission lines. And that transmission line impedance is given by this square root of r plus I omega L over g I omega and so on. So these are some characteristic properties of the transmission lines. And for the vacuum, it will be just the root of mu 0 over epsilon 0, or it will be equal to E over H, which turns out to be about 377 ohms, because these are fundamental constants. Okay. So this is the impedance of vacuum, and because this is represented in terms of E and H, it is often customary to write the Poynting's theorem or Poynting's vector as E cross H rather than 1 over mu 0 times E cross B. The two are numerically absolutely equal, of course, right? So this is also the principle behind laser cooling and Bose-Einstein condensation and so on. All right. So the electromagnetic energy actually physically pushes an object. Okay, just the way you can push this table, right, and do work on it at a certain rate, which will determine the power that you are delivering to the system. It's exactly the same mechanics that we have worked out over here, except that the agency is not a mechanical tool or a hammer, it is electromagnetic energy. So the sun's light pushes the dust particles in comets, which is why the tails of comets are always pointed away from the sun, wherever the comet is on the orbit around the sun. The comet is not trailing the nuclear mass of the comet, it is pointing away from the sun. Okay? It is not along the orbit, it is not trailing the nuclear mass, it is always away from the sun. So when the comet is here, the tail is pointing away from the sun. When the comet is here, it is pointing away from the sun. It is not pointing in this direction, it is pointing away in this direction, from the sun to the comet and away from it. Okay? And this is the principle which goes into slowing down atoms. So you can take an atom, shine light on it from this side, and it imparts momentum on it. So it is like a physical collision of two objects, and this is going to slow down this object. It can push it in this direction, but then you have another laser beam from this direction and trap it in between. It might escape to the top or bottom. You have two laser beams from the top and bottom, and like this. So you can sort of trap it and slow down these atoms, and if these atoms are bosonic, you can nudge them into condensation. So these are wonderful physics comes out of this, but I'll stop here, I'll take some questions.
Like we see that in different fields of physics, as time passes, new things come up and advancements are done, but in this electromagnetic field theory or electrodynamics, did it get saturated up to this Poynting theorem and all? I mean, anything recent additions to this field?
Well, the Bose-Einstein condensation is 20 years old.
Okay, so that is also part of electrodynamics.